Hello children, welcome to online classes. Today we will discuss important points from chemical kinetics and radioactivity. Now, it is a branch of chemistry which deals with the study of rates of chemical reactions and the factors which determine their rates. So, it is a branch of chemistry which deals with the study of rates of chemical reactions and the factors which determine their rates. Let us start with the rate of reaction. So, meaning of rate of reaction. Rate of reaction is the change in the molar concentration of one of the reactants and products per unit time. So, rate is the change in the concentration of reactants or products per unit time, and mathematically it is represented as rate is given by plus or minus dc by dt. Plus or minus dc by dt. Here dc stands for the change in the concentration and time dt stands for the time we have, time interval. So dc by dt is the change in the concentration of reactants, dt per unit time we have. And coming towards plus or minus sign. As the time runs, the concentration of reactants gets reduced. Therefore, minus sign is used to express with respect to reactants now. And as the time runs, concentration of the products will be increasing, and therefore plus sign is used to express with respect to products we have. Therefore, finally plus or minus dc by dt is used so that it includes both. Now, for a reaction A plus 2B giving rise to 3C plus 4D, the reaction rates are related as rate is equal to minus dA by dt is equal to minus 1 by 2 dB by dt and plus 1 by 3 dC by dt and plus it is 1 by 4 dd by dt we have. So the minus signs are there with respect to reactants A and then B, and plus signs are coming with respect to products C and then D we have. And coming towards dA by dt, if you take only dA by dt and then dB by dt, these two terms, they are called rate of disappearance of A, rate of disappearance of B. Similarly, if you take dC by dt and then dd by dt, these two terms are called rate of appearance of C and rate of appearance of D we have. So, without dividing by the respective coefficients, you are going to get rate of appearance, rate of disappearance. If you divide with respect to coefficients, we are going to get the rate of reaction. This is regarding meaning of the rate of reaction. Then comes the graphs which are representing the rate of reaction. So as we already seen, plus sign signifies increase in the concentration of the product formed, and minus sign signifies the decrease in the concentration of reactants used. And coming towards units, since it is a change in the concentration per unit time, so concentration units by time will come. So concentration is moles per liter by second. Or as in SI units, it is a mole per meter cube per second we have. If at all you have a gaseous components, then you are going to use atmospheres per second then now. So for aqueous solutions, units are mole per liter per second, and for gaseous components, units are atmospheres per second is used to express the rate of reaction. And if you see the graphs here, now suppose R is giving rise to P, means reactants are giving rise to products for us now. As the time runs here, the concentration of the reactants will be decreasing. Thereby you can see a decrease in the graph coming for reactants now. So this stands for the concentration of reactants now. And as the time runs, the concentration of the products will be increasing, and therefore this graph shows the concentration of the products order we have. So this is a graph representing how the rates of how the concentrations of reactants and products are changing with respect to time. Next one, the factors which are influencing the rate of reaction. First one will be the nature of reacting substances. So ionic reactions are very fast when compared to covalent reactions, because in the case of ionic reactions, only rearrangement of ions are taking place and therefore they are fast. When it comes to covalent reactions, at the time of reaction, the existing bonds have to break and new bonds have to form. It takes certain period of time, therefore covalent reactions are slow. So finally, ionic reactions are fast and covalent reactions are slow. When it comes to temperature, the rate of reaction increases with increase in temperature. This can be dealt in detail in the coming slides now. So remember, rate of reaction is always increasing with increase of temperature, whether it can be endothermic reaction or else it can be even exothermic reaction also. Coming towards concentration of reacting substances. Rate of reaction increases with increase in concentration of reactants. Of course, except we have here zero order reactions are exceptional here. In the case of zero order reaction, rate is completely independent of the concentration. In all other reactions, rate depends upon the concentration. When concentrations are increased, rate is going to be increasing. Then coming towards effect of catalyst. A positive catalyst always increases the rate of reaction, whereas a negative catalyst will be decreasing the rate of reaction. So factors affecting nature of reactants, temperature, concentration of reacting substances, and catalyst we have. These are the factors affecting the rate of reaction. Then comes law of mass action. Law of mass action, that is at constant temperature, it says that the rate of a chemical reaction is directly proportional to the product of active masses of reactants, each raised to the power equal to its stoichiometric coefficient in balanced chemical equation. It was proposed by Goldberg and Wage. Once again, the law of mass action states that the rate of a chemical reaction is directly proportional to the product of active masses of reactants, each raised to the power equal to the stoichiometric coefficient in the balanced chemical equation. And here the active mass is nothing but molar concentration, that is moles per liter or else moles per decimeter cube we have. Or if you take gases, it's a partial pressure, nothing but Newton per meter square, or it can be atmospheres we have. So therefore active mass stands for the concentration only, expressed in terms of moles per liter or as in terms of atmospheres we have. This is regarding law of mass action. Let us take up a reaction, say 2A plus 3B giving rise to here say C and 4D we have. Let us write the rate of reaction according to law of mass action. So rate is given by K into A square into B to the power of 3 we have. So here 2 is nothing but coefficient of A here and 3 is a coefficient of B here now. So this is according to law of mass action. Rate is given by K into A to the power of 2 into B to the power of 3 we have. And active mass is a molar concentration only. Active mass means number of moles by volume in decimeter cube we have. This is regarding law of mass action. Then comes the meaning of specific rate. The rate constant or specific reaction rate or velocity constant. Now for a reaction, the rate constant can be defined as rate per unit concentration of reacting substances. Rate per unit concentration of reacting substances we have. Means when, for example, when you take a reaction like say A plus B giving rise to products here now. So rate is equal to K into concentration of A say into concentration of B we have now. If you take A and B as 1, then K becomes equal to rate only. So therefore K is defined as a rate per unit concentrations of these two substances. So rate constant can be defined as rate per unit concentration of reacting substances. K depends on temperature and a catalyst for a given reaction. Means if you increase the temperature, rate will be increasing, thereby rate constant also increases. And if you add a catalyst, rate will be increasing, then also K will be increasing for us. Implies that K depends upon the temperature as well as catalyst we have. Rate is independent of initial concentration or pressure. Since we are defining K per unit concentrations, definitely it is going to be independent of initial concentration or initial pressure we have. And it indicates what? Larger the value of K indicates that rate is going to be higher, means faster the rate of reaction. So higher the value of K means higher the rate of reaction we can say. This is regarding the rate constant or velocity constant or as specific reaction rate. Then comes to the molecularity of a reaction. Now when you take an elementary reaction means a reaction which happens only in one single step, that is called elementary reaction. So in the elementary reaction, the molecularity is total number of reactant molecules present in the balanced equation. For an elementary reaction means happening only in one single step. In such elementary reaction, molecularity means total number of reactant molecules present in the balanced chemical equation itself is called molecularity of a reaction. When it comes to a complex reaction means reaction taking place in more than one step is called a complex reaction. In the case of complex reaction, each and every single step has its own molecularity. In the case of a complex reaction, there are multi-steps in that. So each and every step has its own molecularity in the case of complex reaction. And it is given by the mechanism of the reaction. Molecularity comes from the mechanism of reaction, and molecularity cannot be fraction or zero, and it is always a whole number. Cannot be a fraction or zero, and the value cannot be more than 3. Implies that we have 1 or 2 is the molecularity of any reactions we have, because it's not more than 3. Rarely we have 3. So 1, 2 and 3 are the possible molecularity of reactions. Always a whole number, cannot be a fraction value, cannot be zero, comes from mechanism, means it is nothing but a theoretical concept we have. This is regarding the molecularity of a reaction. Then comes order of a reaction. The sum of the powers to which the concentration terms are raised in the rate law itself is called order of a reaction. Sum of the powers to which the concentration terms are raised in the rate law itself is called order of reaction. It is always an experimentally determined quantity. Doesn't come from a theoretical concept. It's only experimentally determined quantity we have. Suppose we have a reaction like this: A moles of A plus B moles of B, giving rise to, say, products now. Now rate law will be given as rate constant K into A to the power of X into B to the power of Y here now. A power X and B power Y we have. The terms X and Y, that is the powers in the rate equation X and Y, need not be the coefficients of A in the balanced equation. Because these powers X and Y are in the rate law are determined from the experiment. They are given by the experiment here now. Whereas A and B in the equation are obtained by balancing the equation. So here powers X and Y are coming from the experimental data, whereas A and B are obtained by balancing the chemical equation. So these two may or may not be same. So therefore, the sum of the powers means, now in this case here, X plus Y itself is called order of reaction. So sum of the powers to which the concentration terms are raised in the rate law itself is called order of a reaction, and X and Y are experimentally determined quantity, and they are not coming from the balanced equation. This is regarding order of reaction. Let us take for a reaction A giving rise to products P now. Say time T is equal to 0. Let us take A is a concentration of reactant A. At time T is equal to T, suppose X moles are reacting. Implies we are left with only A minus X after a time T we have. Implies X is the amount reacting for us now. X moles are reacting here, and we are left with A minus X we have. Now the rate of reaction, rate is always given by change in the concentration per unit time. So starting with A, we have now A minus X means X moles are changing now. So X moles are reacting. So rate is given by dx by dt, amount of change, which is also given by rate constant K into A minus X whole to the power of N we have. Now here this is nothing but, this is called differential equation. Dx by dt is nothing but rate of reaction. K into A minus X to the power of N. X is the amount reacting in a time T we have. N stands for the order of reaction, which itself is called differential equation. Now, if you are integrating the differential equation here, we are going to get different equations, that is, we are going to get different integrated forms we are going to get now from this. So, for example, if you take in this case, say if at all N is equal to 0, say for zero order reaction, then rate will become equal to K into everything becomes 1 only, because anything power 0 became 1. So rate became equal to rate constant K. That implies that rate of reaction is completely independent of the concentration of reacting substances in the case of zero order reaction we have. So in the case of zero order reaction. So when you are integrating the differential form, we are going to get the integrated forms of the various equations. Those things can be derived and finally you are going to get a table of this form. So here we have integrated rate equations for different reaction orders. So zero order reaction, K is equal to A minus X by T, or simply we can write K is equal to X by T also in this case, is also equal to X by T here now. Coming towards units of the rate constant K, we can take general form as units of rate constant K is equal to, it will be molar seconds inverse, that is moles per second per moles per liter per second by molar to the power of say n here, where n is the order of reaction. When you take a zero order reaction here, n is equal to 0 here now. N is equal to 0, this becomes 1. So units will be molar seconds inverse or else mole per liter per second we have. And coming towards half-life period, by substituting A minus X as A by 2 half, you are going to do the expression A by 2K. So for zero order kinetics, rate constant K is equal to X by T and half-life is equal to A by 2K we have. Implies half-life is proportional to initial concentration. Then first order kinetics, K is equal to 2.303 by T into log of A by A minus X here. And units are seconds inverse. Substitute here, say in this expression, n is equal to 1 now. So therefore m and m gets cancelled. We are left only with the seconds inverse. So here is seconds inverse we have. And half-life is given by 0.693 by K. Second order reaction, K is equal to X by 80 into A minus X we have. And again substitute here value 2 in this case now. You are going to get this expression liter per mole per second, and half-life is given by 1 by Ka. So these formulas we need to remember while solving the problems. That is a zero order reaction, K is equal to X by T. Zero order reaction, half-life is A by 2K we have. First order reaction, K is equal to 2.303 by T into log of A by A minus X, half-life is 0.693 by K. Second order reaction, K is equal to X by AT into A minus X, and then 1 by Ka is a half-life of second order reaction. So these formulas should be remembered while solving the problems. Then when you go to the fractional order reactions here, fractional order reaction, the rate of reaction is independent of the dependent on the fractional power of the reactants we have. In the case of fractional order reactions here, the rate of reaction depends on the fractional power of the reactants. So for example, H2 and Br2 giving rise to 2HBr, rate is equal to, rate law is given as H2 to the power of 1 and then Br to the power of half we have. Sum of these two powers is 3 by 2. So for this reaction we say that order of reaction is equal to 3 by 2 because sum is equal to 1 and then half we have. Similarly, other reactions, CO plus Cl2 giving rise to COCl2. The total order is being found to be 5 by 2 here. And CHO, CH3CHO, acetaldehyde giving rise to CH4 and CO, it is being found to be 3 by 2. These three are the examples given to us as the fractional order reactions. So the examples we need to remember, because which are the following having fractional orders, they may ask in that way also. So H2 plus Br2, CO plus Cl2, acetaldehyde giving rise to. These are the examples for the fractional order reactions. Then comes the pseudo order reactions we have now. Pseudo order reactions here, the reactions, first of all, meaning of this one, pseudo order reactions whose actual order is different from expected order from rate law itself is called pseudo order reactions we have. Pseudo order reactions means the reactions whose actual order is different from that expected from the rate law itself is called pseudo order reactions. So for example, they can take first order reactions whose molecularity is 2 or there more than 2 we have. Suppose when you take a reaction like hydrolysis of ester or inversion of sugar, let us see the reaction like this. Say ester or COOR dash plus water giving rise to acid plus alcohol we have. Now for this, the expected rate law, the expected one. The expected rate law is equal to rate constant K into concentration of RCOOR into that of H2O we have. Since water is taken in large excess, the rate will be independent. The rate will be independent of the concentration of this. So therefore now the actual rate law, that is rate is given by K dash into concentration of ester we have. Concentration of ester. Here K dash will be equal to K into concentration of H2O. So this will be another constant because you are taking excess of the water, the concentration. It will be 55.5 molar. So this always remains constant. Now this is said to be a pseudo first order reaction. Actually order appears to be 2. Order appears to be 2 because of these two components that are involving the reaction. Appears to be 2, but actually order is 1. Such type of reactions are said to be pseudo order reactions. So pseudo order reactions means reactions whose actual order is different from that expected from rate law itself is called pseudo order reactions here. The next how to find out the order of reaction, various methods we have. First one is a graphical method, applicable only if you have one reactant. Only you have one reactant. The integrated rate equation expression of the various orders are converted into y is equal to mx plus c form, means straight line form, and a graph of a function of concentration against the time is drawn. The order of the reaction corresponds to the expression which gives the straight line. So here what we are doing is we are converting the integrated rate constant expressions into the y is equal to mx plus c form, and then we are comparing, we are plotting a graph between the concentration versus time t. If you get a straight line that corresponds to that particular order of reaction. For example, if you take a zero order reaction, rate constant K is given as A minus x by T. Zero order now. Let us bring this into the y is equal to mx plus c form. Y is equal to mx plus c form. So that is to say Kt is equal to A minus x here. Bring this to other side now. So A minus x is equal to minus Kt plus A we have. We take this as y-axis is equal to mx plus c now. Implies when you plot the graph here, on this axis is y minus x here now. It is time t in this case. We get a graph of this type here, and slope of this graph is equal to minus k. So when you are plotting a graph for log a minus x and time t, if you get a straight line having a negative slope, then that can be said to be a zero order reaction. In this way, we are going to change the integrated expressions into form y is equal to mx plus c, and we are going to plot the graphs. This is an example taken for this zero order reaction example we have. Similarly, for all we can derive the expressions. So a minus x versus t, straight line stands for a zero order reaction. If you plot log a minus x versus t, a straight line, then that is said to be a first order reaction. If 1 by a minus x versus t, straight line, that is said to be a second order reaction. All these things are obtained from the rate expressions which are given in the table previously. So take the equation, bring in the form of y is equal to mx plus c, you are going to get straight lines in these cases. This is regarding determination of order of reaction, which is called graphical method. Next one, Ostwald's isolation method we have. In Ostwald's isolation is applicable for 2 or more than 2. So graphical method applicable only for one component system. It is applicable for 2 or else more than 2 components we have. This method involves the isolation of one of the reactant by taking all other reactants in large excess. So here principle is, if you take a component in excess, the rate is going to be independent of the component which you are taking large excess quantity. Suppose you have two components, say A plus B, giving rise to product P we have now. Now if you take A in excess, suppose if A is in excess, then rate will be independent of A. And then we can find order with respect to B, we can find out. So we are taking A in excess, then the rate will be independent of A So now we can find out the order of reaction with respect to B. In second case, we can take B in excess, then rate will be independent of B, then you can find out order with respect to A. Then you can add those two orders. So in this method involves isolation of one of the reactant by taking all other reactants in large excess, because rate will be independent of the reactant which we take in excess quantity. So you can find out in that way. Let us take here. So the order with respect to the reactant is determined, means that which you are taking limited amount. The process is repeated for all other reactants. Finally, sum of the powers of all the reactants gives rise to the order of the reaction. So we isolate one among them. This is regarding isolation process. Then comes half-life method we have. This is said to be half-life method. Half-life method. So in this method, half-life proportional to 1 by A power n minus 1, where n is the order of reaction here. A stands for the initial concentration there now. So n is the order, A is initial concentration. So we will be changing the initial concentration, we will be finding out the half-life of that reaction. And then we are going to get order by this formula. N is order of reaction given by 1 plus log T2 minus log T1 by log A1 minus log A2. Here T2 is a half-life when initial concentration is A2 we have, and T1 is a half-life when you have initial concentration as A1 we have now. So N is equal to 1 plus log T2 minus log T1 by log A1 minus log A2 we have. Where here the principle used is half-life is proportional to 1 by A power n minus 1. In that way, this can be used to find out the order of reaction. Then, the effect of temperature on the rate of reaction. It is experimentally found that for every 10 degrees rise in temperature, the rate of reaction doubles to triples. Means it varies from 2 times to 3 times we have. For every 10 degrees rise in temperature, rate of reaction almost it doubles to triples. Means varies from 2 to 3 times now. The ratio of rate constant of reaction at a particular temperature to the rate constant of the reaction at a temperature 10 degrees below is called temperature coefficient. At a particular temperature and then 10 degrees below, the rate constant's ratio itself is called temperature coefficient we have. So we suppose you have taken at 30 degrees Celsius, 30 degrees Celsius rate constant. Now we can take temperature coefficient as it should be K30 by K20 itself is called temperature coefficient of the reaction. Now difference must be 10 degrees. This will be 10 degrees lower, this will be 10 degrees higher we have. So mathematically you can write here K, it is T plus 10 by KT we have. This will be nearly equivalent to 2 to 3 times we have. And it's called temperature coefficient of the reaction. Then the relation between the T and then K is given by Arrhenius equation. Given by the Arrhenius equation, where the K is given by A into e to the power of minus EA by RT. E to the power of minus EA by RT. And if you take logarithmic forms, finally you are going to get log K is equal to minus EA by 2.303 into 1 by T plus log of A we have. When you plot a graph for this, so the graph means here you are taking log K here and 1 by T means Y here M X plus C we have. So we have taken X axis as a 1 by T value there now. Y axis we have taken log K now. So we are going to get a straight line having negative slope because negative value is there now. Slope is going to be negative for us now. So for this value, slope is equal to minus, it is EA by 2.303 into R we have. That is the slope now. So Arrhenius equation gives the relation between the rate constant K and the temperature of the reaction. So these are the two forms to remember. That is a exponential form as well as the logarithmic forms. And graph we are plotting with a log K and 1 by T. We are getting a slope, negative slope, and slope value is equal to minus EA by 2.303 into R we have. Then in two different temperatures, if you take the same expression, we are going to get like this. Log K2 by K1 is equal to EA by 2.303 into R T2 minus T1 by T1 T2 we have, where K2 is the rate constant at a temperature T2 we have, and K1 is the rate constant at temperature T1 we have. Regarding log K2 by K1 is equal to EA by 2.303 into T2 minus T1 by T1 T2 regarding Arrhenius expression. Then comes catalytic influence on the rate of reaction. The presence of a positive catalyst alters the reaction path in such a way that it will be decreasing the energy of activation. Thereby, rate will be increasing for us now. A positive catalyst will be decreasing the energy of activation and increases the rate of reaction. If you take a negative catalyst, this also alters the rate of reaction by changing the path of reaction now. That is, in such a way that it will be increasing the energy of activation and thereby decreasing the rate of reaction. So, catalyst is always altering the path. So, a positive catalyst alters the path, means it alters such a way that it is decreasing the energy of activation and increasing the rate of reaction. Negative catalyst means this also alters the path such a way that it is increasing the energy of activation and decreases the rate of reaction. Then comes the collision theory of reaction rates we have. According to this theory, the collision theory of reaction rates, a chemical reaction takes place due to a collision between the reactant molecules. Means without collision, a reaction cannot happen according to collision theory of reaction rates. And for these collisions to be effective in nature, there are two things. Reactant molecules must possess required energy to react. And then reactant molecules must have proper orientation. So, unless collisions are taking place, reactions cannot happen. There's one point here. Then the collisions must have required amount of energy. Third point is that they must have proper orientation. Then the reaction will be fruitful. Now let us take meaning of the energy terms involved in the collision theory of reaction rates. The minimum energy that reactant molecules must possess in order to form products is called threshold energy. The minimum energy that reactant molecules must possess in order to form products is called threshold energy. And the excess amount of energy required by reactant molecules so as to attain threshold energy is called activation energy. The excess amount of energy required by the reactant molecules so as to attain threshold energy is called energy of activation. Energy of activation can be given as ET, threshold energy, minus average energy of reactant molecules. So EA is given by ET minus average energy of reactant molecules. Let us see a graphical representation for this. That is to say, when you take on this axis energy on this axis, and say path of reaction on this axis. Now let us suppose this is energy of reactant molecules. Let us put it as ER, energy of reactant molecules. So they must attain energy so as they react, means the graph goes like this. So this value can be taken as ET, means threshold energy. The energy is from here to here. It's called threshold energy now. Then here the reaction takes place and products are being formed. And may suppose the graph is coming like this. Now this value can be taken as energy of production now. So right from here to here, this is called ET. This is called threshold energy. And then this is called average energy of reactant molecules. This part is called average energy of reactant molecules. Now difference between the energy of reactant molecules and threshold energy, this value, this gap, this is called energy of activation. This is called EA for us. So EA will be equal to ET minus energy of reactants. And this is the energy of products we have. This difference can be taken as delta H also. Means energy of products minus energy of reactants we have. So if it is say backward reaction, then these are the reactants, these are the products will come. So this is the energy diagram we have. To understand energy of activation, threshold energy, energy of reactants, energy of the products, and delta H of the reaction we have. Then, so according to molecular collision theory, the rate is given by Pz into e to the power of minus Ea by Rt. So P is called orientation factor, because the theory says that it depends upon the molecules which are properly oriented also. So orientation factor means the fraction of the molecules properly oriented for effective collisions. So there must be collisions, they must be properly oriented, they must have energy also now. So P stands for orientation factor. Z is the collision frequency we have, means number of collisions made by the molecules per unit time, collision frequency. And e to the power of minus Ea by Rt is also known as Boltzmann factor, Boltzmann factor, and is a fraction of molecules having energy equal to or more than E. That is a fraction of activated molecules. So there are three things in collision theory. So P orientation factor, Z collision frequency, e to the power of minus Ea by Rt, the fraction of molecules having energy equal to or more than that of E. That is nothing but fraction of activated molecules we have. So then the reaction takes place. Now coming towards for an endothermic reaction and exothermic reaction. So for endothermic reaction, the same graph you can take like this. For endothermic reaction, the energy of products will be more, thereby the graph comes like this. The endothermic reaction here now. So endothermic reaction is the energy of reactants, energy of the products we have, and here threshold energy, and this will be energy of activation. And say if it is a reversible reaction, then from here to here the reaction takes place now. Thereby this part means from here to here now. This will be taken as energy of activation, but for backward reaction. Let us put EAB here now. This will be EAF then. So in the case of endothermic reaction, energy of activation of forward reaction, you take from here to here, forward reaction, from here to here, this point, is greater than energy of activation for backward reaction. This part is called for backward reaction energy of activation now. And if it is say for exothermic reaction, it is going to be reversed then now. For exothermic reaction, it comes the other way. That is to say, this will be exothermic graph we have. So energy of activation for backward reaction comes from here to here then now. This is called energy of activation from here to here. EA backward reaction, forward reaction we have. Difference, this is more than that. So delta H value can be taken like this. Energy of activation for forward reaction. So EAF minus, you can take EAB as a formula to find out delta H value. EAF minus EAB also gives the difference of delta H values. Then comes radioactivity. Since radioactivity follows first order kinetics, radioactivity problems can be solved using first order relations only. So formulas will be remaining same as that of the first order relations because radioactivity follows first order kinetics. Thank you. Today we will discuss the properties of p block elements and their compounds. Let us now begin with 15th group elements. 15th group elements include nitrogen, phosphorus, arsenic, antimony and bismuth. They are including nitrogen, phosphorus, arsenic, antimony and bismuth. And their general configuration is NS2NP3. The hydrates and oxides of these elements are poisonous in nature. Hence, these elements are called nicogens. The word nicogen, the term nicogen, is derived from ancient Greek word which means choking or suffocating. Because these hydrates are suffocating in nature, these elements are called nicogens. So nicogens are 15th group elements. Their configuration is NS2NP3. They include nitrogen, phosphorus, arsenic, antimony and bismuth. Now anomalous properties of nitrogen. Nitrogen has a small size, high electronegativity, high ionization energy a non-availability of d orbitals. This property is going to be common for all elements. In all groups, the property is common. The first element, always smaller size, high electronegativity, high ionization energy, a non-availability of d orbitals. It exists as diatomic gas with a triple bond between two nitrogen atoms. So nitrogen can form p-pi multiple bonds because of small size, and therefore it can form n triple bond. Due to high bond dissociation energy, it is highly stable and is chemically inert now. So triple bond is having more energy and therefore it is chemically inert. But the single NN bond is weaker than single PP bond present. That is, the nitrogen is small in size, so the non-bonding pairs, so when you take nitrogen atom, the two smaller in size now, so when these two form a single bond here, the non-bonding pairs which are present, they come close to each other now, and then they cause repulsions, they undergo repulsions. The repulsive force will decrease the bond strength. So the single NN bond is weaker when compared to single PP bond because of high inter-electronic repulsions of non-bonding electrons. When it comes to phosphorus, the atom is larger size. Though it has same number of electrons here, electron density will not be much, thereby repulsive force between the non-bonding pairs of phosphorus will not be much. Hence, it is having a stronger bond when compared to nitrogen. Nitrogen has a unique ability to form p-pi bond. The formation of p-pi bond depends upon the size of the atom. Smaller sized atom can form always multiple bonds with p-pi bonds with itself as well as with the other elements now. And nitrogen cannot show pentavalency as it does not contain d orbitals in that. The other elements can form p-pi d-pi bonds. Others can form p-pi d-pi bonds. Others cannot form p-pi bonds. So the p-pi bond formation depends upon the size. Small sized atoms can form p-pi bonds. And larger sized atoms cannot form p-pi bonds. Then next one. Coming towards hydrates of this group. The general formula of the hydrates is MH3. So they can be like this: NH3, NH3, then PH3, AS, S3, SB, H3, BiH3. They are having general formula of MH3 we have. Let us see the properties of these hydrates now. Stability. Stability decreases down the group. The stability of these hydrates, because all molecules are covalent in nature, it depends upon the strength between the M and H bond. So the strength of this bond depends upon the size of the atom now. The size of the atom is increasing across the group. It is increasing down the group. So thereby the extent of overlapping will be decreasing now. Hence bond strength decreases. Thereby stability of these hydrates decreases down the group. Reducing strength. When the stability is decreasing down the group, they can lose hydrogen much easily now. Thereby reducing strength is increasing now. Basic nature. All have electron pairs. All have electron pairs on them. Therefore, all the molecules are electron pair donors. Implies all are nothing but Lewis bases now. The electron pair donating property depends upon the availability of electron pair on the central atom. As the size of the atom increases here now, availability of the pair gets reduced. Thereby, basic strength decreases down the group. Coming towards boiling points now. Boiling points among covalent molecules depends upon the molar mass. More the molar mass, more the van der Waals forces, more the boiling point. Therefore, we can see BiH3 being higher molar mass, having higher boiling point. But when it comes to ammonia is exceptional because ammonia is having hydrogen bonding. Thereby ammonia comes exceptional here now. So highest boiling point is BiH3 and least boiling point is PH3. This is the order of boiling points. Then shapes now. All hydrates have pyramidal shape due to Sp3 hybridization of central atom now and presence of the lone pairs of the electrons on it. So only sp3 means it should be having tetrahedral structure. Because of the lone pairs which are present now, it becomes no pyramidal shape now. Coming towards bond angles decrease and reach to 90 degrees due to pure p orbitals involving down the group. Down the group we can see that pure p orbitals involving for the formation of hydrates, whereas for ammonia, nitrogen will be sp3 hybridized. So all hydrates are pyramidal in structure due to the sp3 hybridization and the lone pair of electrons. Bond angles are getting reduced to 90 degrees because down the group pure orbitals start involving in bond formation. So this is the order of bond angles we have. Ammonia bond angle being highest and bismuthine bond angle being the least we have. This is regarding hydrates. Excuse me. All these elements form two types of oxides. Trioxides M2O3 and pentoxides M2O5 we have now. And we know that down the group metallic nature of these elements are increasing, thereby the basic nature of the oxides will be increasing down the group. So first two oxides are acidic in nature, that is both trioxides and pentoxides. First two of them are acidic in nature. Next two of them are amphoteric in nature, and last is basic in nature. That is to say, the metallic properties increasing down the group, thereby the oxides properties changing from acidic to basic. So first two acidic oxide, next two are amphoteric oxides, and then last one is a basic in nature we have. Now let us see the structure of these trioxides and pentoxides now. Let us see the structure of nitrogen oxides. So trioxides and pentoxide structure. Now the trioxide can be taken as it is a structure of NO plus NO2, because structure is N2O3 have. Trioxide means it can be taken as a mixture of NO and NO2 structure. So that is NO, we have a lone pair here, and then NO2. NO2 is structure of N2O3 molecule now. When you take N2O5 molecular structure, it can be taken as two NO2 units joined together through one oxygen atom now. So two NO2 units are there. So NO2 unit, and then we have one more NO2 unit this side then now. So two NO2 units are there, and bonding through one oxygen atom we have now. We have one oxygen atom between these two. This is the structure of N2O5 molecule. So trioxide and then pentoxide we have. When it comes to phosphorus oxides, say trioxide of phosphorus, which is a P4O6 structure. So phosphorus, then oxygen atoms which are tetrahedral, and again you have phosphorus here, phosphorus here now, and then between these two one more bond is present. Here one more POP bond is there, and here you have one more bond. So altogether we are, and then each phosphorus has one lone pair of electron on that. So basic unit is called a tetrahedral unit we have. It is having POP bonds are there. It contains POP bonds, and each phosphorus is having three bonds. POP bonds are there, three for each phosphorus atom. When you take phosphorus pentoxide, which is a P4O10, so therefore similar structure we have phosphorus, oxygen, and then here also we have phosphorus here, phosphorus atom, phosphorus here now, another POP bond between these two, one more POP here, one POP here now, and each phosphorus has one double bond here now, one double bond here, one double bond here, and one double bond here we have. The structure of P4O10 structure. P4O10 is having P double bond O's are there, and each one is tetrahedrally bonded here, phosphorus atom. Tetrahedral structure here, each corner. So without lone pairs here, only oxygen will be having lone pairs. These are the structures of the oxides of phosphorus and nitrogen. Then halides now. All elements form halides. All are forming halides. Actually, two types of halides are there, trihalides and pentahalides. So all are forming trihalides now. Except BiF3, all other halides are covalent in nature. All others are covalent molecules now. BiF3 is coming under ionic molecule. Rest of them are covalent in nature. All trihalides undergo hydrolysis. That is, all trihalides undergo hydrolysis here. And all trihalides have pyramidal shape. Suppose when you take, say, PCl3 molecule, a trihalide structure, pyramidal structure we have. So phosphorus and then 3 chlorine atoms here. We have the clear chlorine atoms and we have a lone pair of electron present on that. So molecule comes under pyramidal structure. So here among trihalides also all undergo hydrolysis except NF3 molecule. NF3 is supposed to be more stable. There is a reluctant towards hydrolysis there now. Then when you take phosphorus trichloride, it is obtained by passing dry chlorine gas over heated white phosphorus. So phosphorus, white phosphorus plus Cl2 giving rise to PCl3 you have. So here 6 and then 4. So we are passing dry chlorine gas over heated white phosphorus. It can also be prepared by action of thionyl chloride on white phosphorus. Thionyl chloride is SOCl2. So P4 plus thionyl chloride SOCl2 also gives us PCl3. Other byproducts are SO2 and then S2Cl2 we have. So it is also obtained by the action of thionyl chloride on white phosphorus. So P4 SOCl2 giving rise to PCl3. Byproducts are SO2 and then S2Cl2 we have. Regarding preparation of phosphorus trichlorides. Coming towards the properties now. It's a colorless oily liquid and hydrolyzes presence of moisture. So PCl3 plus water gives rise to H3PO3 phosphorus acid and byproduct is HCl we have now. So during hydrolysis reactions here, the oxidation state will not change. It is +3 here. It remains here also same plus the state we have now. So PCl3 undergoes hydrolysis and forms here H3PO3. In PCl3, it is a phosphorus is Sp3 hybridized. It has a pyramidal shape due to lone pair of electrons. The structure already we have seen in the previous slide. That is a phosphorus having 3 bonds and chlorine atoms here. And we have here a lone pair of electron on that. So one lone pair, it becomes pyramidal and Sp3 is Sp3 hybridized phosphorus we have. Nitrogen does not form pentahalides because of the absence of d orbitals and the maximum covalency of nitrogen is only 4. Pentahalides are more covalent than trihalides. See, pentahalides will be having +5 oxidation state now. According to Fazan's rules here, more charge always leads to more covalent character. So pentahalides having +5 oxidation state here, whereas trihalides have only +3 oxidation state. Hence, +5 state compounds are having more covalent character. Then, regarding pentahalide preparation now, is again obtained by passing dry chlorine gas on white phosphorus. It must be excess of dry chlorine gas then now. So P4 plus Cl2. It should be excess here now. So PCl5, the chlorine should be excess. Then we are going to get PCl5 now. It is also prepared by the action of SO2Cl2 on phosphorus. Not SOCl2, SO2Cl2 on phosphorus. So phosphorus plus SO2Cl2 sulfuryl chloride giving rise to, it forms PCl5 and byproduct is SO2 we have. I am not balancing the equations. I am writing main products in these reactions. So phosphorus on action with SO2Cl2 sulfuryl chloride gives rise to PCl5 plus SO2. Then its properties: PCl5 is yellowish white powder and in the moist air it hydrolyzes to POCl3 first, and finally it changes into phosphoric acid. So phosphoric acid has +5 state here now, oxidation state, and PCl5 has +5 state. So during hydrolysis we can see that the state retains the same. So first of all it is forming POCl3. So PCl5 with water forms POCl3 first. Again with excess of water, POCl3 changes into H3PO4. So we can say now PCl5 finally becomes now H3PO4. When PCl5 is heated, it sublimes. But heated high temperature and strong heating, it gives PCl3 and Cl2. So PCl5 is a sublimating solid. It sublimes, but heating very strongly, it dissociates to PCl3 and then PCl5 we have. These are the properties of PCl5. Then coming towards structure. In PCl5, the phosphorus is Sp3d hybridized. It has a trigonal bipyramid structure in the gaseous form as well as in liquid form. The bond angles are PCl5 are 90, 120, 180. Let us see the structure of the molecule. So hybridization is Sp3d hybridization. Structure is trigonal bipyramid structure. Angles are 90, 120, 180 we have now. So the structure of the molecule, that is a trigonal bipyramid structure we have. We have here phosphorus in the middle we have, and these are Cl atoms. Okay, so bond angles 90, that is to say in the planar angles you can take like this. Between these two we have an angle of 90 degrees here now. 120 means these angles are 120 degrees here. 180 means the entire angle between these two will come 180 degrees for us now. The axial bonds are angle 180 degrees we have. This is a case of gas phase. Is having gas phase and liquid phase, we have same structure. In solid state, the molecule exists as PCl4 plus and then it is PCl6 minus we have. The solid state. So it is ionic compound in solid state we have. It is existing as PCl4 plus PCl6 minus. PCl4 6, this will be tetrahedral part. This is going to be octahedral part we have. So in the gaseous phase, it is trigonal bipyramid structure. Solid phase, we have tetrahedral units as well as we have octahedral units are there. Coming towards oxyacids of nitrogen and respective structures now. So what we have to remember in oxyacids of nitrogen now? In all oxyacids of nitrogen, nitrogen has one OH group. It has one OH group and then one doubly bonded oxygen we have. One NOH group and one doubly bonded oxygen we have, except for hyponitrous acid. So only having different structure hyponitrous acid. That is, we have nitrogen, N2 is there, so double bond, and we have two OH groups now. So there are two H2, N2, O2. We have a lone pair of electron here. It's also having one more type of structure. So it's having both anti and syn forms are there for hyponitrous acid. Because of double bond here, rotation is not possible. So two different forms are there for, that is H2, N2, O2. Now nitrous acid. So what we have to see is, we have one double bond NO and definitely we have one OH group. So therefore nitrogen, we have one double bond O is there and then we have one OH group here. Still we have one more lone pair present on that. The structure of nitrous acid HNO2, that is a HONO we can say, or else. Then nitric acid, the same point must be remembered. Each nitrogen is going to have definitely one double bond O is there. We have one OH group is there and then still we have one more oxygen left and that is going to be a coordinate covalent bond with oxygen we have. HNO3 molecule. In pernitric acid, we have a peroxy bond that is present. Peroxy bond is there. So again we have nitrogen. One double bond is there. We are going to get a peroxy bond. OO bond is there in this one, no peroxy bond. And again you have a coordinate covalent with oxygen we have. These are the structures of oxyacids of nitrogen. Then structures of now oxo acids of phosphorus. So here in all the structures, phosphorus is tetrahedrally bonded. Phosphorus is tetrahedrally bonded we have, and each phosphorus contains one P double bond O and at least one POH group is there in that. And depending upon the formula, it can have one pH group also. So phosphorus is tetrahedral in all the structures here. It has one P double bond O and at least it has one POH group now. Let us see the structures. Say phosphorus acid. So phosphorus acid here, P. One double bond O should be there. And we have say one OH group here now. One OH group is there. So with this we have done with two oxygens now. We have one more oxygen that is present. Implies we have there one more OH group is there. And still we have here one more hydrogen present. Implies that we have one hydrogen bonded to phosphorus then now. So implies the phosphorus acid is having two OH groups and one hydrogen now. And hydrogen bonded to phosphorus is responsible for reducing property of the molecule. So OH groups are responsible for oxidizing properties. H is responsible for reducing property, and basicity of this acid is only 2 because we have only 2 OH groups for this. Then comes hypophosphorus acid. Again phosphorus, we have one double bond O is there. It must have one OH group here. With this, two oxygens have been used up. We have remaining two hydrogens left, implies we get here two more hydrogens bonded for this. So it is only monobasic in nature. Then comes pyrophosphorus acid now. This can be assumed that by taking two molecules of phosphorus acid, that is to say H3PO3 phosphorus acid, you take two molecules of this and subtract from one H2O from this. Then you are going to get H4P2O5, pyrophosphorus means. So taking two molecules of phosphorus acid, removing one water molecule. So let us see the structure now. So P should have one double bond O. There are two P atoms. Double bond O we have. Each P must definitely have one OH group. One OH group. One OH group is there now. So with this we are left with only one oxygen atom, odd number of oxygen atoms. So these are bonded through the oxygen atoms here. And still we have two hydrogens left here. Therefore here is H and then here you have H here now. So there are only two OH groups for this. It is also dibasic in nature and molecule contains one POP bond. So pyrophosphorus contains one POP bond in that. Next, let us take now phosphoric acid groups. So principle is same again. So we should have phosphorus atom, doubly bonded oxygen atom will be there and OH group here now. Still we have here two more oxygens left and two more hydrogens are there. That implies you are going to get two more hydroxyl groups for this. So implies it is going to be a tribasic in nature. Now pyrophosphoric acid. Again take two phosphoric acid groups and remove one water molecule from them. Now here there are two phosphorus atoms here. So phosphorus and take one double bonded oxygen atom there. It must have definitely one OH group for each one now. And again it's also having odd number of oxygens are there. Therefore is bonded through one oxygen atom. And still we have here two more hydrogens and two more oxygens are there. Implies that both must have two more OH groups then now. So it implies that it is a tetrabasic in nature now. It is also having one POP bond. Metaphosphoric acid. The molecule is taken n times means it exists as a cyclic structure, it's a cyclic form. Let us take for example trimer, taking n is equal to 3. So there must be only 3 phosphorus atoms then, 3 means here. So phosphorus and phosphorus now. Each P has one double bond O. We have here one OH group here. So one double bond O and one OH group here. Again here also one double bond O and we have here one OH group now. And between these phosphorus atoms join with one POP bond. So POP bond and then POP bond we have. This is going to be a cyclic trimeric structure we have. It can have even n is equal to 4, means you can draw tetramer, hexamer, pentamer and so on and so forth we have. So metaphosphoric acid exists as a cyclic structures, not planar forms. With this we have done with the all oxyacids of phosphorus. Then preparation of nitrogen. In the laboratory, nitrogen is prepared by action of ammonium chloride with sodium nitrite. That is to say, ammonium chloride NH4Cl plus sodium nitrite, that is NaNO2. The main compound is N2 gas plus the byproducts are NaCl plus H2 we have. So N2 can be prepared by the action of ammonium chloride on sodium nitrite NaNO2. It is also prepared by thermal decomposition of ammonium dichromate. So ammonium dichromate, that is NH4 taken twice, Cr2O7 dichromate, on strong heating gives rise to N2 plus chromic oxide plus water. So it is also prepared by thermal decomposition of ammonium dichromate. Then comes pure compound. Very pure N2 can be obtained by thermal decomposition of barium or sodium azide. So azide will be N3 minus is called azide now. Azide ion is there. And N minus 3 is called nitride ion. This is nitride ion. Azide ion we have. Now barium azide. So Ba N3 taken twice we have. On strong heating gives elements, that is it forms barium plus it forms nitrogen. So very pure N2 can be obtained by thermal decomposition of sodium, or else you can use barium azide. With this we have done the preparations of nitrogen. Then properties of nitrogen. It is a colorless, odorless, tasteless and non-toxic gas. The two stable isotopes 14 and then 15 we have now. And with elements like lithium and magnesium, it can form nitrides. So lithium nitride forms magnesium nitride now. It combines with hydrogen to give ammonia, presence of ion catalyst, and then promoter molybdenum. Nothing but it is a Haber's process we have. It also combines with oxygen at high temperature to form nitric oxide. And liquid N2 is used as a refrigerant to preserve biological material and then food items now. So once again here, so colorless, tasteless, odorless gas we have. Important properties are it combines with hydrogen to form ammonia. That is the Haber's process we have. It also combines with oxygen at high temperature to form nitric oxide. And liquid nitrogen is used as a refrigerant to preserve biological materials and food items. Then comes ammonia preparation. Ammonia is prepared from decay of nitrogenous organic matter. Decay of nitrogenous organic matter in the nature. When it comes to chemical reactions here, any ammonium salt with a caustic soda use ammonia gas. Let us take common ammonium salt, ammonium chloride plus calcium hydroxide, giving rise to liberation of ammonia gas plus calcium chloride and H2O we have. So any ammonium salt with caustic soda or calcium hydroxide uses ammonia gas. Then coming towards commercial preparation, on large scale ammonia is prepared by Haber's process. As per Lee chart test principle, the favorable conditions for the preparation of ammonia are given to us. Low temperature is maintained, but you are maintaining an optimum value of 700 to 750 Kelvin. High pressure 200 atmospheres is maintained. Catalyst is divided ion we have, and promoter is molybdenum or oxides of potassium and aluminium. So ammonia is done by large scale by Haber's process. So we need to remember all conditions: low temperature, high pressure, catalyst and promoter. Temperatures are 700 to 750 Kelvin, 200 atmospheres we have, and catalyst is finely divided ion, and promoter is molybdenum or else oxides of potassium and then aluminium. Then properties. Ammonia is a colorless and with a pungent smell gas. Colorless gas with pungent smell, and the freezing point is 198.4 Kelvin and boiling point is 239.7 Kelvin we have. It has a higher boiling point when compared to pH 3. That is because ammonia is having intermolecular hydrogen bond. So ammonia is a colorless, pungent smell gas. It is having higher boiling point when compared to PS3 because it is having intermolecular hydrogen bond. Ammonia is a Lewis base and very good ligand and forms complexes with the compounds of metal ions. So for example, if you take copper ions, say for example like copper sulfate, it reacts with ammonia and forms a complex. It forms Cu NH3 taken 4 times. It's a deep blue in color. This complex is deep blue color we have now. So it forms a complexing agent. So ammonia is an electron pair donor. Suppose when you take silver halide, solid substance, with ammonia, silver ion also forms a complex here, Ag NH3 taken twice it forms, plus and Cl minus it forms. This is completely soluble one. A soluble complex is being formed. Silver diamine chloride is being formed here now. In that way, ammonia forms a complexes, a very good complexing agent we have now. Then comes brown ring test now. Brown ring test for a nitrate salt, freshly prepared ferrous sulfate solution is taken. So for nitrate salt means we take a test tube, it should be in a slanting position. We take a test tube like this. And here a salt solution is taken, means nitrate salt should be taken there now, having a nitrate ion. And then they will be adding freshly prepared ferrous sulfate solution. We have a ferrous sulfate solution here now. So there is a FeSO4 solution is added. And then along the walls of the test tube, they are going to add sulfuric acid now. They will be adding sulfuric acid. At the junction of these two layers, we can see brown color now. Junction we can see some brown color formation, brown layer can be seen. So freshly prepared ferrous sulfate is added to nitrate salt. Then H2SO4 along the walls of the test tube is being added there. We can see a brown ring at junction of two layers. So that is to say nitrate salt is being added to ferrous sulfate solution. And nitrate salt gets reduced to NO there now. And then it forms nitroso-ferrous sulfate. This itself is brown color. Nitroso-ferrous sulfate is the formula of the complex here. This is a brown in color. Then phosphorus. Phosphorus has 3 allotropic forms. There are white phosphorus, red phosphorus and black phosphorus. White, red and black we have. Now the white phosphorus has individual discrete tetrahedral units and a P4 structure. That is, we can take like this tetrahedral unit. So atoms are 4, another unit. So all of them are individual discrete units present with a bond angle of 60 degrees now. Because of this bond angle 60 degrees, the molecule is having bond angle strain and therefore white phosphorus is highly reactive in nature. When it comes to red phosphorus, it is having a polymeric P4. Polymeric P4 units are present in that. Means, let us take one unit like this, one more unit, one more, and so on and so forth we have here. Say taken n times will come. In each corner we have a phosphorus atom that is present here. Like this we have. The polymeric structure now. Say taken n times. It's a polymeric form. Because of polymeric structure, the red phosphorus is less reactive in nature. When it comes to black phosphorus, is having a highly polymeric structure. Highly polymeric structure when compared to even red phosphorus also. So thermodynamically it is even more stable when compared to red phosphorus. Then comes phosphine gas. Phosphine gas is prepared by the action of calcium phosphide on water or else with dilute HCl. So calcium phosphide Ca3P2 plus, let us take HCl, giving rise to calcium chloride plus PH3, phosphine gas now. But when compared to phosphine and ammonia, these two gases both are hydrates of same group elements only. Ammonia is a very good complexing agent, whereas phosphine is not a good complexing agent there. There's a basic difference between ammonia and phosphine. Now let us discuss the properties of 16th group elements and their compounds. 16th group includes oxygen, sulfur, selenium, tellurium, polonium. These elements are found in ores and minerals. So the elements of the group are called chalcogens. Chalcogens stands for ore forming elements are called chalcogens. So for example, hematite ore, Fe2O3, pyrolusite ore, MnO2, zinc blend, ZnS, CuFeS2 and barium sulfide. All are the ore forming, all are the ores. So these are all ore forming elements, hence they are called chalcogens. Let us take general properties of 16th group elements. The oxygen is the second most electronegative element in the periodic table. The first one is fluorine and second element is oxygen we have. Fluorine, that is electronegativity is 4 units we have, and oxygen electronegativity is equal to 3.5 units. Second element, second most electronegative element. Due to the small size of the oxygen, it has a lower electron gain enthalpy when compared to sulfur. Now here the important point to remember is first electron gain enthalpy of sulfur is more than that of oxygen. Means oxygen being small size has more electron density. It repels the incoming electron more. Thereby oxygen is having less electron gain enthalpy. That is a first electron gain enthalpy. When you are going to the second electron gain enthalpy, oxygen is having more when compared to sulfur now. Because O minus ion requires more amount of energy to add one more electron. Hence it requires more energy. So therefore, first electron gain enthalpy, sulfur is more than oxygen. Second electron gain enthalpy, oxygen is more than sulfur. These are the important properties and general characters of these elements. Then coming towards oxidation states, these elements exhibit -2, +2, +4, +6 oxidation states. And due to high electronegativity of oxygen, it always shows the states of -2, except with the fluorine. In fluorine compounds, it exhibits positive oxidation states. Say in OF2, it is having +2 state, O2F2 it is having say +1 state. Except in fluorine compounds, oxygen always exhibits a negative oxidation states now. And oxidation state of oxygen peroxides is -1. So these are all exceptions. So normally it exhibits only -2 oxidation state, and in fluorine compounds it shows positive states, and in peroxides it shows -1 oxidation state. Remaining elements sulfur, selenium, tellurium usually show +4, +6 oxidation states in their compounds now. So remaining, that is sulfur, selenium, tellurium normally show +4 and then +6 oxidation states now. This is regarding oxidation states of these elements. Then comes atomicity, number of atoms in the molecule now. Atomicity of sulfur is 8. So there is S8. It both in rhombic sulfur as well as monoclinic sulfur, it is octatomic molecule only. It is having crown shape, that is to say it comes like this, crown shape molecule. So it will be crown shape. So atoms here. So like a crown shape molecule. And the higher temperature, the crown shape, that is S8 rings, start breaking and exist as S6, S4 rings also. S6 rings will be having say a chair form, that is the structure comes like this, having chair form, and S4 will be tetrahedral structures we have. So S8 will be crown structure, S6 will be a chair form now. At very high temperatures, normally more than it is 1000 Kelvin, it exists as S2 molecule. Like you can take oxygen molecule, means it will be in this form, which is similar to oxygen molecule. So atomicity of sulfur is 8. It has basically crown shaped structure. At higher temperatures, it starts breaking down into S6, S4 forms. S8 crown structure, S6 is having chair conformation. Very high temperature, it molecule further breaks down and exists as Es2, which is something like oxygen molecule. Then anomalous behavior of oxygen. Oxygen has some anomalous behavior when compared to the rest of the elements in the same group. Now, this is due to small size and high electronegativity. So oxygen is having smaller size and high En values. Because of these two, it has a different properties. Due to the small size and high electronegativity of oxygen, strong hydrogen bonds are present in water, which is not found in other hydrates of the same group. Now, so because of high electronegativity, so hydrogen bonds are present in water, whereas hydrogen bond is absent in other hydrates of same group. And oxygen doesn't have d orbitals, hence it limits its covalency to 4. In practice, the valency of the oxygen is rarely it exceeds 2. So normally it restricts its covalency because of the absence of d orbitals. So because of smaller size, high electronegativity, it is forming very strong hydrogen bonds here in water. Others are not having hydrogen bonds. And because of the absence of d orbitals here, it can't expand the octet configuration further. Next comes hydrates of these elements now. So the properties of the hydrates. First point is regarding thermal stability. It always decreases down the group. Thermal stability depends upon the bond strength. Since all molecules are covalent in nature, in covalent molecules, thermal stability depends upon the extent of overlapping. So here we have general formula. Suppose you take it as say H2M, something like say H2O and so on and so forth here. So it depends upon the bond strength between M and then H there now. So it depends upon the extent of overlapping between the orbitals here now. And extent of overlapping here depends upon the size of the central atom here now. When size of the central atom is increasing, extent of overlapping gets reduced. Thereby bond strength gets reduced. That implies stability starts decreasing now. So in the case of covalent molecules, we need to see the stability means here the strength of the bond, and that depends upon extent of overlapping, and that extent of overlapping will be decreasing down the group, and thereby stability decreases down the group. Reducing properties increasing now. When the stability is decreasing, they can very easily give hydrogen, and thereby reducing property starts increasing there. Now acidic character. These compounds, say except water, are having acidic property. Suppose when you take water, say H2O plus H2S if you take now, H2S gives proton to H2O now. Implies it exists as H3O plus and then it is SH minus we have. So it's a proton donor, nothing but an acid molecule. This proton donating property will be increasing down the group. So acidic strength is increasing down the group because of the bond strength is decreasing down the group. The order of boiling points of these hydrates. Boiling points of covalent molecules will depend upon the van der Waals forces. In turn, they depend upon the molar mass. Higher molar mass is going to have always higher van der Waals forces. Thereby, boiling point is going to be higher. But exception is water molecule here, because water molecule is having stronger hydrogen bonding. Other than water molecule, remaining will follow a general trend, we can say. Means higher the molar mass, higher the boiling points. Exception is water is having highest among them because of hydrogen bonding. So the water has higher boiling point than rest of the hydrates and exists as liquid at room temperature because of intermolecular hydrogen bonding that is present. Intermolecular hydrogen bonding is there in water. These are the properties of the hydrates. Thermal stability is decreasing because of decreasing in the bond strength. Reducing property increases because bond breaks very much easily. Acidic strength is also increasing because once again the strength of the bond is decreasing. Boiling points that basically depending upon the van der Waals forces, in turn depending upon the molar mass. Only exception is water because of its hydrogen bond. These are the properties of hydrates. Then comes oxides. So they form two types of oxides here, dioxides and trioxides. We can take it as MO2 and then MO3 type of oxides we have. The acidic strength If you take dioxides, SO2, SeO2, TeO2, and trioxides, SO3, SeO3, TeO3 we have. Whenever oxidation state is same, the acidic strength depends upon the electronegativity. Highly electronegative element is going to be forming a stronger acidic oxide. So thereby SO2 is a stronger acidic oxide. Similarly in trioxides also we see the same trend is being formed. But when you compare acidic strength of say trioxides and dioxides here now, trioxides are having more acidic strength, means we can say SO3 is having more acidic strength when compared to SO2 we have. So when comparing these two, trioxides are more acidic nature when compared to dioxides. Then the first one, sulfur dioxide molecule. So sulfur dioxide is formed by burning sulfur in air. So simple equation, S plus O2 on burning gives rise to SO2 here. Roasting of sulfide ores also gives sulfur dioxide as a byproduct. Suppose when you take zinc sulfide, so roasting in oxygen, that is excess of air now, then we get zinc oxide plus byproduct as sulfur dioxide. So roasting of sulfide ores also gives rise to sulfur dioxide gas now. Then in the laboratory it is prepared by treating sulfide salts with dilute sulfuric acid. Sulfide salts are taken, means you can take an example of sodium sulfide salt, Na2SO3, with sulfuric acid, say H2SO4, giving rise to, it forms Na2SO4 plus sulfur dioxide plus it forms H2O. So sulfur dioxide is formed by the action of sulfuric acid on sulfide salts in the lab. Let us take now the properties of sulfur dioxide. Sulfur dioxide is colorless and pungent smelling gas. The smell of burning sulfur. It dissolves in water to form sulfurous acid. That is, SO2 dissolves in water. It gives rise to H2SO3. It forms sulfurous acid. And it reacts with NaOH, forms a sodium sulfite. So when you take sulfur dioxide, say dissolving in sodium hydroxide, it forms there Na2SO3. Sodium sulfite is being formed here. So you can take it as acid and base type of reaction. So that is SO2, acidic oxide, NaOH, basic in nature. It forms sodium sulfite salt. Next, it reacts with the chlorine to form addition compound, which is known as sulfuryl chloride, SO2Cl2. Simple addition reaction only, that is SO2 plus Cl2, it gives rise to SO2Cl2. We have sulfuryl chloride. And when come to the moist sulfur dioxide, behaves as a bleaching agent as well as reducing agent also. And one property is the bleaching action of sulfur dioxide is because of reduction. Bleaching property is because of reduction. It is acting as a reducing agent also. Now coming to a structure. Structure of sulfur dioxide is having a bend shape, and sulfur is undergoing Sp3 hybridization and bond angle is 119 degrees we have. So sulfur, we have two double bonds, oxygen atom, a lone pair upon this we have. And sulfur is undergoing Sp2 hybridization and bond angles are here 119 degrees we have now. So bend shape and Sp2 hybridized molecule. Then halides and respective structures of the compounds here now. Halides and the structures. So 16th group elements form four types of halides: Mx6 hexahalides, Mx4 tetrahalides, Mx2 dihalides, and Mx, but they are existing as dimers, that is monohalides of M2X2 type we have now. Coming to the structures of these molecules here, to find out the hybridization, we require total number of bond pairs plus total number of lone pairs are required now. The total number of bond pairs and lone pairs will give us hybridization. Let us take for example Mx6 now. So M is being 16th group element, has 6 electrons here. It is forming 6 bonds altogether. It implies that Mx6 has completely 6 bond pairs are there. 6 bond pairs means hybridization will be Sp3d2. Total number of pairs will give us hybridization. totally we have 6 bond pairs are there. So hybridization is equal to here Sp3d2. Let us take an example, say SF6 molecule in that way. So SF6, so structure Sp3d2 hybridization, sulfur in the middle, all corners are occupied by fluorine atoms. So if you take SF6 molecule now, it comes in this way. So structure is octahedral structure. Octahedral structure. And it is sulfur is undergoing here Sp3d2 hybridization we have. This comes number of bond pairs plus lone. There are no lone pairs here. All of them are bond pairs only. Now let us take Mx4. Right? Mx4, the central atom, let us take for example SF4 molecule. SF4 molecule. Sulfur is having 6 valence electrons here. So let us take 1, 2, 3, 4, 5 and 6 valence electrons. There are 4 bonds towards 4 halogens. Let us take these are the 4 bonds here. 4 bonds are being formed. And still we have one more lone pair. So number of bond pairs are 4 here. 1, 2, 3, 4 and one lone pair we have now. So total number of pairs, lone pairs plus bond pairs is equal to 5 we have. If it is 5, hybridization is going to be Sp3d hybridization. So total number of pairs will decide hybridization. Total number of pairs, if they are 6 in number, that is going to be Sp3d2. If they are equal to say 5, that is going to be Sp3d we have. If there are total number of 4s are pair, it is going to be Sp3 and so on and so forth. Total number of pairs will decide hybridization. In this case, we have 4 bond pairs are there and 1 lone pair we have. So 5, it comes to Sp3d hybridization. Let us see the structure now. So the basic form, that is Sp3d structure, comes like this. And a lone pair is present in the equatorial plane here. Let us take remaining, all of them are fluorine atoms like this. So here we have a sulfur atom present in the middle. So this structure, so Sp3d hybridization is coming at a seesaw structure. It is a seesaw structure we have. One lone pair on equatorial plane, remaining are the bond pairs we have now. So total number of pairs are 5. So it is coming under Sp3d hybridization. Let us now take Mx2 structure. In Mx2 structure here, suppose sulfur is having again 6 valence electrons here, of which 2 of them are bonded here now. So let us take metal M here now, element M, 6 electrons. So 1, 2, 3, 4, 5 and 6. These 2 are forming bond with halogen now. Implies number of bond pairs are 2, number of lone pairs are again 2. Total number of pairs are coming to 4 in this case. Total number of pairs are 4 means it is Sp3 hybridization. So molecule is bend shape, means we have metal M and X and X here we have and 2 lone pairs are there. Something like we can say SO, something like H2O structure. So bend shaped molecule we have. And M2X2 type of structure. It is similar to that of H2O2 structure. Structure is like you can take H2O2, which is open book structure. Along the spine of the book, we have the 2 elements which are present here. Means if you take the spine of the book, say metal element here now, and here we have X and X. These 2 are in the 2 leaves of the book. Now if you expand this structure, we can take a structure coming like this. So something like open book structure of say H2O2 structure, that is oxygen atoms in the spine of the book and leaves contains 2 hydrogen atoms. So something like similar to that of H2O2 structure we have. These are the structures of halides now. Excuse me. Then oxo acids of sulfur. Sulfur has many number of oxo acids in which it is Sp3 hybridized, and in all oxo acids basicity is 2. Basicity is 2 means all structures definitely have 2 OH groups in that. So 2 OH groups are there in all molecules. Now there are 4 series of acids here. So sulfurous acid series, sulfuric acid series, thionic acid series and peroxide acid series we have. There are 4 series of acids. But in all acids, sulfur is Sp3 hybridized here, and basicity is 2 means we have definitely 2 OH groups are there. and at least at least sulfur is having one double bond O will be there, and at least it definitely each sulfur has two OH groups in that. There are two OH groups, and then we have one S double bond O. Minimum S double bond O is there. Based on this, we can work out the structures of these molecules now. Let us take one by one. Sulfurous acid series now. So basic sulfurous acid means H2SO3, the first molecule, H2SO3. So sulfur dibasic, so definitely it must have two OH groups. All acids have two OH groups there, and sulfur at least has one double bond O. It's nothing but H2SO3 form, sulfurous acid now. Now comes thiosulfurous acid. If you are replacing one oxygen say by one sulfur, those compounds are called thiosulfurous acid, thio compounds. Let us take the same structure here. You are replacing this oxygen by sulfur here, and so this molecule is called now thiosulfurous acid. So H2, it will be S2, and then O2 we have. We have replaced one oxygen by one sulfur. H2S2O, it is thiosulfurous acid we have. Then pyrosulfurous acid. The compound pyro means we need to take 2 units of sulfurous acid and remove one water molecule from them. Then you are going to get pyro acids now. We are taking 2 units of sulfurous acids and remove one water molecule from them. It is having here pyrosulfurous acid is going to have 2 sulfur atoms in that. So let us write 2 sulfur atoms in that. And E is dibasic acid, so it should be totally it must have 2 OH groups in that, and each is having one double bond O here now. And since molecule is H2S2O5, we have one more oxygen present, that is going to be double bond O here now. This structure of pyrosulfurous acid. So pyro acids can be assumed that they are obtained by a removal of one water molecule from 2 units of sulfurous acids. Then comes dithionous acid. Dithionous acids. Dithionous acids means they have a group called sulfinic group. Sulfinic group. Sulfinic group is SO2H group. SO2H groups are called sulfinic group. Sulfonic is SO3H. Sulfinic is SO2H. If 2 sulfinic groups are bonded to each other, that is said to be dithionous acid. Dithionous acid. So here, so there are once again double bond O, each sulfur has one OH group now. So molecule is here H2, it is S2 we have, H2S2 and then O4, which is called dithionous acid. So dithionous acid has sulfur bonding, and there are 2 sulfinic groups. Sulfinic group is SO2H group is there. So these 4 are coming under sulfurous acids now. So sulfurous acids are the basic sulfurous acid, then comes thiosulfurous acid, then comes pyrosulfurous acid, then comes dithionous acid. Then sulfuric acid series we have. The basic compound is sulfuric acid, that is H2SO4 we have. So again there are 2 OH groups because all of them are dibasic in nature. We have 2 more oxygens left, 2 double bond O we have. That is a sulfuric acid structure. Thiosulfuric acid. Again replace one of the oxygen by sulfur. Implies that it should be H2S2O3. You are replacing one oxygen by sulfur. So therefore in structure also just replace one of the oxygens by sulfur. And you are going to get thiosulfuric acid. Then pyrosulfuric acid we have. So again it can be assumed that from 2 units of sulfuric acid, remove one water molecule, you are going to get pyrosulfuric acid. It is also known as by other name oleum, that is H2S2O7. One more name is oleum for this one now. Oleum. Excuse me. Now again one double bond O must be there, each sulfur atom. There must be definitely 2 OH groups altogether we have now, and we are still left with oxygen atoms. So it's having odd number of oxygen atoms, so one comes in between these two then now. So H2S2O7 oleum structure is this. Oleum is actually supposed to be a mixture of sulfuric acid plus sulfur dioxide. So H2SO4 plus SO3 oleum structure. Then comes thionic acid series now. Thionic acid series contain sulfonic groups. That is, they have SO3 H groups are there, which are bonded through sulfur atoms. Sulfonic acid groups bonded through sulfur atoms there now. Let us take the simple one, say dithionic acid. Means we have two sulfonic groups. So this is SO3H group, sulfonic group. One more sulfonic group we have. Both are bonded to each other. This is called dithionic acid. So formula comes out to it is H2S2. Oxygens are 1, 2, 3, 4, 5, 6 we have. 5, 6 we have. Now when you take trithionic acid, it must have one more sulfur atom now. We have two sulfurs here, one more sulfur comes in between now. Means remaining structures same. So we have like this, one sulfonic group here. We have here one more sulfonic group. Add a sulfur atom between these two. That is called now trithionic acid then now. If it is a tetrathionic acid, add two more sulfur atoms there now. So suppose we have tetrathionic acid. The structure comes here, one double bond over here, sulfonic, sulfur and sulfur, and then here one more sulfonic group we have. This is called tetrathionic acid. So thionic acid, thionic groups or sulfonic groups are SO3H groups. They are bonded through sulfur atoms. If they are directly bonded, it is called dithionic. One sulfur atom between them, tri, two, tetra, and so on and so forth we have. So we can take the formula as H2, say S2 plus N here, and O will be 6 we have. This N is 0 in this case we have. N is 1 here we have. N is 2 in this case we have. That way we can get thionic acid series now. Then comes finally peroxo acid series. Peroxo series will have peroxy bonds which are present in them. So peroxy bonds are there in that. And peroxy monosulfuric acid means it has only one sulfonic group is there, and then we have one peroxy bond in that. So one sulfonic group SO3H. So SO3H we have. It must have one peroxy bond also. So OH now. It is called peroxo monosulfuric acid. It is H2SO5. One more name is Karos acid. It is also called Karos acid now. So this is the peroxy bond present in that. Peroxo disulfuric acid means it must be having two sulfonic groups, but it has only one peroxy bond, as in the case of Karos acid. So two sulfonic groups, SO3H groups here, one peroxy bond here, one more sulfonic group we have. This is H2S2O8 we have. One more name is Marshall acid. This is called Marshall acid now. So H2S2O8 is Marshall acid. It's a peroxy acid series because we have a peroxy bond in that. So sulfur finally forms four types of acid series we have. That is, let us see. Four series are sulfurous acid series, sulfuric series, thionic series, and peroxy acid series we have. Next one, coming towards ozone. Preparation of ozone, that is O3. When a slow, dry stream of oxygen is passed through silent electrical discharge, we can get ozonized oxygen is being formed. So O2 passing through, subjected to silent electric discharge, we get O3. And thermodynamically, O3 is not stable with respect to oxygen. That is reason behind is whenever O3 decomposes, so O3 say giving rise to say O2, it will be 2 and 3 here now. This is going to be definitely exothermic in nature. So this well delta H is going to be negative for this one now. So the process delta H is negative and delta S value will be positive for this one now. Because number of moles are increasing, delta H is positive for this. These two results, that is delta H negative, delta S positive, will make a large negative value for delta G. they will make a large negative value for delta G, and thereby reaction progresses towards the dissociation of O3 molecule. Hence we say that O3 is thermodynamically less stable when compared to that of oxygen molecule. Then comes properties. Pure ozone is a pale blue color gas, and dark blue liquid we have, and violet black solid we have. So gas molecule, pale blue, liquid state, dark blue, solid state, violet black we have. And the concentration of ozone rises above 100 ppm, then it becomes difficult to breathe. So then coming towards, it's a very good oxidizing agent because of liberation of nascent oxygen. O3 easily gives rise to O2 plus oxygen. Because of this, it's having oxidizing properties now. Let us see the oxidizing properties of ozone. Some of the oxidizing reactions of ozone. It is oxidizing lead sulfide to lead sulfate. Lead sulfate here. It oxidizes potassium iodide to iodine we have. Potassium iodide to potassium iodine. And then mercury to mercurous oxide. It's actually known as tailing of mercury. Means when you are passing mercury through a glass tube, when you are passing ozone through a glass tube containing mercury, what happens is mercury loses meniscus and touches the walls of the glass tube. It touches the walls of the glass tube because of the formation of mercurous oxide. The phenomena itself is called tailing of mercury. Means losing the meniscus and touching the walls is called tailing of mercury. And then regarding depletion of the ozone layer. So this NO is released by Z planes, and directly it acts upon the ozone and forms NO2 plus O2 here now. So means it is one of the reasons for the NO is the reason for the depletion of ozone layer. Then the coming towards structure. The molecule is angular one, bond angle is 117 we have. Bond lengths are equal because of the resonating structures. We can take the structures like this. So oxygen molecule, and one of them is going to be coordinate bond here now. And then another structure, it will be the other way. So coordinate bond here and then double bond here you can take. So resonating structures of these two, and thereby bond lengths are equal, and both are equal to 1.28 angstrom units, and bond angle is 117 degrees we have. And it is used as germicide, disinfectant, bleaching agent, and oxidizing agent. If you see these three properties, disinfectant, bleaching agent, and oxidizing agent, all three are because it is liberating nascent oxygen. Very good oxidizing agent. So because of the nascent oxygen only, is having these three properties, which are disinfectant, bleaching, and oxidizing properties now. Then comes sulfuric acid preparation, its properties now. Sulfuric acid is one of the most industrial chemical used worldwide, and is manufactured by contact process. The principles used in the contact process is burning of sulfur or sulfide ores to generate first of all sulfur dioxide gas, and SO2 is further oxidized to SO3 here, and SO3 is absorbed in H2SO4 to form oleum. That's to say SO3 plus H2SO4 gives rise to H2S2O7, oleum is being formed. And once you get oleum there, means H2S2O7, when you add water for this, on distillation you are going to get back the sulfuric acid molecules. So oleum is dissolved to get, SO3 is dissolved to get oleum there. Oleum is hydrolyzed to get back the sulfuric acid. This is all the sulfuric acid prepared by contact process. Then properties, the colorless, dense, oily liquid is having stronger hydrogen bonds in that, and specific density of 1.84. Dissolves in water with evolution of large amount of heat now. So it's highly exothermic in nature, dissolution in the water. Hence, the concentrated acid must be added slowly to water to prepare dilute acid now. So we cannot add water to acid. We need to add acid to water very much slowly to prepare the dilute sulfuric acid. Then comes the acid is having strong dehydrating property, and it has more affinity towards water molecules there now. It charges the carbohydrates and forms black residue because of its dehydrating property only. Suppose when you take C12, say H22O11, you have taken carbohydrate there, and then presence of sulfuric acid, it should be the concentrated one. It absorbs water molecules completely. It absorbs here 11 H2O molecules, and finally carbon is left off. So we can see a residue of carbon form. It charts the carbohydrates. And then hot and then concentrated sulfuric acid is moderately strong oxidizing agent. It's a moderately strong oxidizing agent. So it both metals and nonmetals are oxidized. Metals as well as nonmetals are oxidized by this. So let us take copper plus sulfuric acid, giving rise to, it forms copper sulfate and then sulfur dioxide plus water we have. If we take carbon, carbon also gets oxidized to corresponding carbon dioxide, and H2SO4 becomes sulfur dioxide plus water. Means both metals as well as nonmetals can be oxidized by this. Now let us discuss properties of 17th group elements and their compounds. 17th group includes fluorine, chlorine, bromine, iodine and astatine. These elements are born from sea salts with most of the metals. So they are called halogens. The word halogens is of two words, halus and gen. Halus stands from sea salt, gen stands from born. So they are born from sea salts, hence called halogens. The general configuration of these elements, halogens, is Ns2Np5. They have 7 electrons in the outermost orbit. Let us take the general properties of these elements. Atomic radii and ionic radii increases down the group. It's a general trend. And here, these are small sized atoms in their respective period because of higher nuclear charge. But still down the group, atomic size will be increasing. Ionization enthalpies, because of more nuclear charge, they are having higher IP values. And once again, IP values decrease down the group. Electronegativity, they are highly electronegative elements in the periodic table, and the order of En values, fluorine being the highest in the complete periodic table. So fluorine, then more than chlorine, then bromine, then iodine, and all the values are according to Pauling scale values only. Electron gain enthalpy, being small size, they have a higher electron gain enthalpy, but exception is fluorine. Fluorine is having lesser value than chlorine because fluorine is small size and has high electron density. When you compare fluorine and chlorine here now, so chlorine is a larger sized atom, whereas fluorine is a small sized atom now. So it is having more electron density when compared to chlorine. It is having more electron density, it starts repelling the incoming electron. Thereby, it has a less electron gain enthalpy. So lesser electron gain enthalpy for fluorine, it is because of small size and then higher electron density. Then coming towards physical properties, color, a fluorine yellow colored gas, chlorine green yellowish gas, bromine reddish brown liquid, iodine violet solid. Violet, it can be called a sublimating solid. Iodine is violet sublimating solid. The bond enthalpies decrease down the group due to increase of their size. Again, exception is fluorine. Because in the case of fluorine, being very small size here, to form fluorine molecule, the fluorine atoms come close and they have non-bonding pairs now. So when atoms are coming close to form fluorine molecule, the non-bonding pairs also come close to each other, and they start repelling with each other. So repulsive force present between these two will decrease the bond strength. So exception is fluorine. Fluorine is having lesser value. That is because of small size, non-bonding pairs undergo more repulsions, and repulsive force decreases the bond strength in this. So order of the bond enthalpies are chlorine more than bromine, then comes fluorine, and then iodine we have. Then the oxidizing power is in the order of. So they are the best oxidizing elements in complete periodic table. Fluorine being the best. Fluorine, then chlorine, then bromine, then iodine we have. So here fluorine is a best oxidizing agent. That is because of its low bond enthalpy as well as higher hydration enthalpy. Fluorine has the highest value because of low bond enthalpy as well as a higher hydration enthalpy. When it comes to oxidation states here, all halogens exhibit -1 oxidation state. And due to high electronegativity and absence of d orbitals, fluorine mainly exhibits -1 state. So fluorine mainly exhibits -1 because of high electronegativity as well as absence of d orbitals. The other elements, chlorine, bromine, iodine, exhibit +1, +3, +5 as well as +7 oxidation states. Now, other elements are going to exhibit positive states, that is chlorine, bromine, iodine exhibit +1, +3, +5 and then +7 oxidation state. Then comes anomalous behavior of fluorine. The anomalous behavior of fluorine is due to its small size, high electronegativity, low bond dissociation enthalpy and non-availability of d orbitals. So 4 points are there. Anomalous behavior of fluorine is because of small size, high electronegativity, low bond dissociation enthalpy and non-availability of d orbitals. Most of the reactions of fluorine are highly exothermic in nature. Since it is most electronegative element, it cannot combine with oxygen to form oxoacids. So oxoacids are not there for fluorine because it cannot combine with highly electronegative oxygen. Then when it comes to hydrates, hydrates are of formula HX type we have. We can take, that is HF, then comes HCl, then HBr, then HI. So general formula of hydrates is HX. Let us see the stability of these hydrates now. Since all molecules are covalent in nature, the stability depends upon the bond enthalpy. Between H and then X we need to see the bond enthalpy. And bond enthalpy depends upon the size of the central atom now. When the size of the atom is increasing down the group, when size increases down the group, the extent of overlapping of the orbitals between the hydrogen and halogen atom decreases. Due to this, bond enthalpy gets reduced, thereby stability decreases. So decrease in the stability is because of decreasing in the bond enthalpy. Reducing property is increasing down the group. Reducing property increases, that is because when bond enthalpy decreases, bond breaks easily and they can give hydrogen easily now. So thereby they are reducing agents as well as reducing strength will be increasing now. Acidic strength is increasing, that is because when you take HCl molecule and you add water to this one, the proton donor, so it exists as H3O plus here, is a proton for this, and then Cl minus ion. This proton donating property will be increasing down the group because we can say decrease of bond strength. Coming towards boiling points, because all molecules are covalent in nature, the boiling points depends basically upon the molar mass of the compounds now. And molar mass of the compounds are increasing down the group. Thereby boiling points have to increase. The only exception is HF, because HF is having hydrogen bonding, therefore the molecule is having highest boiling point. So HCl will be having least boiling point here. Then next higher is HBr you have now. Next higher is HI, and highest is the HF because of the hydrogen bonding. This is the order of boiling points in that. Then among the hydrates, the important property of HCl is formation of aqua regia. HCl forms aqua regia. And importance of aqua regia is noble metals also can dissolve in aqua regia. And aqua regia is 3 parts of concentrated HCl and 1 part of concentrated HNO3. 3 parts of HCl and 1 part of HNO3. So noble metals also dissolve in aqua regia. Suppose when you take the example of gold, let us take the reactions here. HNO3, there is one part of HNO3 and say 3 parts of HCl will give us NOCl plus Cl, chlorine, free chlorine, highly active in nature, plus H2O. When you are adding gold to the mixture here, it reacts with the free chlorine and forms AuCl3, that is auric chloride. This auric chloride starts dissolving in HCl and forms there HAuCl4. It is a water soluble one. This is completely soluble. So therefore gold will dissolve in the aqua regia because of the formation of HAuCl4. HAuCl4 is also known as tetrachloroauric acid. Similarly, we can write reactions for platinum also. Platinum also dissolves in aqua regia. So aqua regia importance is noble metals also dissolve in aqua regia, and aqua regia is 3 parts of HCl with 1 part of HNO3. Then interhalogen compounds. Halogens combine among themselves to form a number of compounds which are known as interhalogen compounds of type, that is XX-, XX-3, XX-5, XX-7 we have. So where X the central atom, the larger atom we can say, X dash is a smaller halogen atom we have. Suppose when you take the first category of say X dash here, ClF, BrF we can take now. ClF, BrF. Coming towards ClF will be something like Cl2 structure, chlorine and then fluorine we have here. So non-bonding pairs. So this is a structure of ClF we have. Then next category, now it is X-3 we have. Example is say ClF3 molecule. ClF3 molecule is having three bond pairs. 3 bonds are there, 3 bond pairs, and 2 lone pairs are there. So total number of pairs always give us hybridization now. So we have here 3 bonds are there and 2 lone pairs are there. Means altogether 5 pairs are there. 5 pairs stands for Sp3d hybridization. So Sp3d hybridization, the structure is, so it has basic form, trigonal structure we have. And then let us take ClF3, the Cl is here now. And in the equatorial plane, you have the lone pair of electrons present there now, equatorial plane. Remaining fluorines are there along the axis as well as one along the equatorial plane. Therefore, structure is a T-shaped molecule. So, number of pairs, how to see the number of pairs means here, chlorine is having totally 7 valence electrons. So, 1, 2, 3, 4, 5, 6, 7 we have. And there are 3 atoms fluorine forming bonds. So it will be 1 fluorine bond here, 1 more here and 1 more here. Means we have here 3 bond pairs are there and 2 lone pairs of left. So therefore it is having 3 bond pairs and 2 lone pairs are there. So total number of pairs are 5. We have 5 pairs, that will be Sp3d hybridization. 6 pairs Sp3d2 we have. 6 pairs stands for Sp3d2 we have. 4 pairs will stand for Sp3 hybridization. That way we can find hybridization and structure. Next category, the molecule is X-5. An example is say BrF5 molecule. Again, when you are trying to find hybridization here now, so Br central atom having altogether 7 electrons here. So 1, 2, 3, 4, 5, 6 and 7 here. There are 5 atoms forming bonds here. So 1, 2, 3, 4 and 5 bonds are there. Implies there are 5 bond pairs are there here altogether. We have only 1 lone pair left. 1 lone pair. Altogether we have 6 pairs are there. No, 6 pairs stands for Sp3d2 hybridization. Therefore, structure will be Sp3d2 hybridization. That is, there is a 1 lone pair present on that. Lone pair occupies here, lone pair here. remaining, or here BrF5 we are taking here. Let us write the Br here and then fluorine atoms here now. So the base is square and we have a pyramid on this time. So we can take it as a square pyramidal structure, but it will be distorted square pyramid structure because of lone pair of electrons which are present in that. Next one. Next structure is X7. Let us take I of 7. So all 7 bonds are there. No lone pairs on that. So there was 7 means it will be Sp3d hybridization we have. So it will be, structure is going to be octahedral, the pentagonal structure. So pentagon we have, and then the central atom is say iodine here now, and all corners are occupied by fluorine atoms. All are fluorine atoms. So this will be pentagonal bipyramid structure. No lone pairs, all of them are bond pairs. So Sp3d hybridization we have. Then comes one of the important point regarding interhalogen compounds. They undergo hydrolysis now. In these reactions here, a small halogen comes out as HX and larger one comes out as oxo acid of that. Let us take for example ClF undergoing hydrolysis giving rise to. Here the smaller one is fluorine, it comes out as HX, that is HF. Larger one is chlorine we have, it comes out as HOCl. So oxidation state will remain same. It is a +1 here per chlorine atom. It also has +1 in this oxy acid now. Suppose when you take ClF3 plus water giving rise to, again smaller one is F, it forms HF plus, larger is chlorine having +3 state here now. It forms an oxy acid where chlorine is having +3 state. It is a HClO2 is having +3 state for this. So all molecules undergo hydrolysis. They form 2 compounds. The smaller one is coming out as HX. The larger one is coming out as corresponding oxo acid of that. With this we have done with interhalogen compounds. Then oxo acids of halogens now. Now oxides of halogens here. All oxo acids of halogen are monobasic in nature. All of them are monobasic. All are monobasic. So all are monobasic means all have only one OH group in that. All have one OH group in that. If you are seeing the structures here, in the structures the chlorine has only one OH group. One single bond OH group is there because all of them are monobasic in nature. And then the chlorine forms double bonds with all other oxygen atoms which are present now. So chlorine forms ClO bonds with all other oxygen atoms present. So in all oxy acids, chlorine has one OH group. Remaining all oxygens form multiple bonds, double bonds with the chlorine atom now. Let us now take the first one, HOCl here now. So OH group, only one OH is there. So it will be Cl and then OH group. Cl and then OH group here. When it comes to in which state it is being formed. Now chlorine, when you take this, is having NS2 NP5 configuration, that is 3s2 3p5 we have. So 3s2, let us take 3s2 3p5. So 3s2, 2 electrons here, and 3p5, 4 and 1 we have. So in ground state, chlorine is having one unpaired electron here. So it can form only one bond. Therefore, hypochlorous acid is formed in the ground state for chlorine. And OCl minus ions are called hypochlorite ions. Hypochlorite ions. Then comes the second one, that is a chlorous acid, HClO2. HClO2, chlorine must be having definitely one OH group is there and one double bond O must be there then now. One double bond O. Then coming towards number of lone pairs which are present on that. We know that chlorine altogether has 7 electrons, of which 1 is used here now. 2 of them are used up here now. 3 are used. Therefore 3, 4, 5, 6 and 7. Implies we have altogether 2 bonds and 2 lone pairs are there. 2 plus 2, 4. 4 pairs are there means it's undergoing Sp3 hybridization. And when you take the ground state configuration is, let's say 3s2. So 3s2 we have 3s2, 3p5 we have. So in ground state, it can form only one covalent bond. But here in the molecule we have altogether, there are 3 covalent bonds are there. So therefore, it must undergo excited state. So one of the p electrons moves towards the d orbital then now. So therefore, the configuration comes out to be, so it will be, now we have 3 unpaired electrons are present, therefore it forms 3 covalent bonds as in the case of HClO2. So therefore, it forms the molecule in first excited state of chlorine atom. So HClO2 forms in the first excited state of the chlorine atom. Now let us see the structure. So there is one double bond, one OH group we have, and the salts are known as chloride salts. Salts are known as chloride salts. Let us take the next one, that is chloric acid. We have HClO3. So always chlorine has one OH group is there. There are 2 more oxygens left off here. So there must be 2 double bonds which are there, and therefore it must be having only one lone pair that is being present. So we have 3 bonds and 1 lone pair, means again 4 are there. 4 means it is going to be Sp3d Hybridization. Because of one lone pair here, that is going to be pyramidal structure. So Sp3 and pyramidal structure we have. Let us take in which state it forms. In the previously we have seen in the first excited state we have here 3 electrons which are present here now. Now let us take that first excited state first. So here we have 2 electrons are there. 2 electrons here. So 1, 2, 3. The first state we have only 3 electrons now. Here it is forming altogether. There are 1, 2, 3, 4, 5 bonds are there. We require 2 more electrons, means 1 more electron gets excited here now. It moves here, means finally you are going to get here, that is here 1 electron, 1, 1, 1 and 1 we have. There are now 5 electrons which are present. It is in the second excited state. It forms a HClO3 now. Now structure is, there are 2 double bonds, 1 OH group. We have 1 lone pair present on this. And the anions are called chlorate anions. Chlorate anions here. Then next one, the last one, perchloric acid, HClO4. So Cl, so we have always 1 OH group. Remaining all must be doubly bonded oxygen atoms which are present there now. So there it implies that there are no more lone pair of electrons on that. So base CT is equal to 1. If you see 4 bonds are there, hence 4 pairs implies Sp3 hybridization. No lone pairs, therefore it is going to be perfect tetrahedral structure now. If you see the previous form here, previous structure, it is a second state we have now. Let us take the second state once again here. In second state here, we have altogether 5 lone electrons are there. It is forming 5 bonds now. But here you require another 2 more bonds, because 6 bonds are there with oxygen atoms and 1 OH group here. Send 1 more to this one here. That is, therefore, all 7 of them are now completely unpaired here. It forms 7 covalent bonds. That is said to be third excited state now. Third excited state we have. So it is a no peroxy bond, though it is called perchloric acid. There is no peroxy bond in this one. So structure is, we have altogether Cl, 1 OH group is there. Remaining all of them are multiple bonds like this. So tetrahedral structure is regarding the oxy acids of chlorine we have. Then comes chlorine preparation properties. First one, prepared from manganese dioxide. So MnO2 with HCl gives rise to MnCl2 plus Cl2 and H2O. So Cl2 can be prepared by the action of HCl on manganese dioxide there. One more reaction is by action of HCl, potassium permanganate also. So KMnO4 plus HCl, this also gives chlorine gas. KCl, MnCl2, Cl2, H2O we have. So action of HCl on manganese dioxide, action of HCl on potassium permanganate, both will give us chlorine gas now. Next, coming towards manufacturing process. One is called Deacon's process. It is by oxidation of HCl by atmospheric oxygen, but in the presence of heated CuCl2. The presence of, we are using CuCl2 at a temperature of 273 Kelvin. Is basically acting as a catalyst there. So therefore it will be HCl plus heating in atmospheric oxygen, and we require here CuCl2. Temperature is 723 Kelvin we have. It forms here Cl2 and then H2O. So this will be on balancing, 4 will come here and then 2 moles will come. So oxidation of HCl with atmospheric oxygen in the presence of CuCl2 at a temperature of 723 Kelvin give rise to chlorine gas. One more is the electrolysis of brine also gives chlorine gas at anode. So brine solution NaCl will give rise to Na plus Cl minus ions we have. In aqueous solution, so Cl minus ions being anions move towards anode. So therefore at anode, Cl minus ions move, oxidation takes place. So liberation of chlorine gas takes place at anode now. At cathode, actually water molecules get reduced at cathode there. So at cathode H2O gets reduced because of the electrons which are given there. It forms H2 and then OH minus ions are being produced here now. So it forms that is liberation of OH minus ions and liberation of H2 gas at cathode. So brine solution upon electrolysis will liberate chlorine gas at anode. Then comes properties of chlorine. It is a greenish yellow gas with pungent and suffocating odor, soluble in water, and it is called chlorine water. Chlorine water on standing for long time loses its yellow color due to formation of HCl and HOCl. So chlorine water contains HOCl in that. And hypochlorous acid gives nascent oxygen responsible for oxidizing and bleaching action of chlorine we have. So when you take HOCl, that is hypochlorous acid which is present in chlorine water, this gives rise to HCl plus nascent oxygen. And this is responsible for bleaching action as well as oxidizing properties of chlorine water. Then reaction with alkalis. So with cold and dilute NaOH, it is forming sodium hypochlorite. That is NaOH plus, if you take chlorine gas, it forms here, it should be dilute and cold conditions. It forms NaCl plus it forms NaOCl plus H2O. This is called sodium hypochlorite. If you take the same chlorine gas NaOH, but NaOH should be in the hot conditions, then it forms chlorate. NaOH plus Cl2 giving rise to, it forms there NaCl plus NaClO3 plus H2O, and this is called chlorate now. And both the reactions are coming under disproportionation reactions only. We can see that the oxidation state of chlorine is increasing as well as decreasing. If you take here 0 state we have, it is becoming here -1 and then +1 in this case we have now, -1 and +1. If you take here becoming -1 and +5 states we have. So both the reactions are examples of disproportionation reactions we have. Then when chlorine reacts with the dry slaked lime, it forms bleaching powder. Say chlorine here plus calcium hydroxide giving rise to, it is forms CaOCl2 dot to H2O. It is nothing but bleaching powder. So with the slaked lime, chlorine gas is giving us bleaching powder. Then reaction of chlorine with ammonia. If you take excess of chlorine with ammonia, we are going to get NCl3, is unstable compound, and HCl it forms. And if you take excess of ammonia, the same chlorine gives rise to ammonium chloride and liberates N2 gas. So excess chlorine gives NCl3, HCl. Excess ammonia, it gives rise to ammonium chloride plus N2 gas. Then coming towards oxidizing properties of chlorine. Chlorine oxidizes ferrous sulfate to ferric sulfate, sulfur dioxide to sulfuric acid, iodine to iodic acid. Let us take the reactions now. If we take ferrous sulfate, say for example, ferrous sulfate FeSO4 in acidic medium, so H2SO4 plus chlorine, this gives rise to Fe2SO4 taken thrice plus HCl you have. So ferrous sulfate becoming ferric sulfate there now. If you take sulfur dioxide and then chlorine, say in water, this forms sulfuric acid now. H2SO4 it forms. Again byproduct is HCl we have. If you take iodine and say chlorine here, iodine and chlorine plus water, this forms here HiO3 iodic acid plus it forms HCl. So in all the cases here Cl2 is becoming now HCl, means is becoming -1 state there now, and others are getting oxidized. These are the oxidizing properties of chlorine molecule. So with this we have come to an end of 17th group elements. Now let us discuss properties of 18th group elements and their compounds. 18th group elements include helium, neon, argon, krypton, xenon and radon. All these are gases, and because of completely filled sublevels, they are chemically unreactive. Hence they are called inert gases or noble gases. They are chemically unreactive because of completely filled sublevels. Therefore they are called inert gases. All the elements except helium have the general outermost configuration NS2NP6. Helium is having 1s2 configuration. 1% of atmosphere contain noble gases. In that, the order of abundance is argon more than neon, than krypton, than helium, than xenon. So, in atmosphere, 1% is of noble gases, and in that the order of abundance is argon more than neon, then krypton, then helium, then comes xenon. Now the general properties of 18th group elements. Atomic radii increases down the group with increase in atomic number, the general trend in any groups. Ionization energy decreases down the group, but due to stable configuration, they have very high ionization enthalpy values. Because of completely filled sublevels, they have higher IP values, but again down the group IP values will be decreasing now. Since noble gases have stable electronic configuration, they have no tendency to accept electrons, and therefore they have large positive values of electron gain enthalpy. So because of stable configurations, they do not have tendency to accept electrons. Therefore, they have large positive values of electron gain enthalpy. Then the physical properties of these elements. All noble gases are monoatomic in nature. They are colorless, odorless and tasteless gases. They are sparingly soluble in water, and they have very low melting as well as boiling points. Because the only type of interatomic interactions present is weak dispersion forces. They have only very weak van der Waals forces, and helium is having the lowest boiling point, which is 4.2 Kelvin. So all noble gases are monoatomic, colorless, odorless, tasteless gases. They are sparingly soluble in water, but solubility increases down the group. They have very low melting and boiling points. That is because they have very weaker van der Waals forces present between these atoms. And helium is having lowest boiling point, and it is 4.2 Kelvin. Then the xenon fluorine compounds. Xenon fluorine compound, that is xenon fluorides, XeF2, XeF4, XeF6. Now, all these are prepared directly from elements itself, that is xenon and fluorine. But the fluoride formed depends upon three factors. Depends upon the ratio of the elements used, as well as temperature and then pressure. The type of the fluoride formed depends upon the ratio of these elements used, temperature as well as the pressure. Now when you take excess of xenon and fluorine at 1 bar pressure at a temperature of 673 Kelvin, the compound formed is XeF2. If you take the ratio as 1:5 at 7 bar pressure and 873 Kelvin, XeF4 is being formed. The ratio is 1:20, then under 60 bar pressure, means higher pressure, and 573 Kelvin, then compound formed is XeF6. So all these xenon fluorides are prepared from elements xenon and fluorine itself, but the compound form depends upon three factors, depends upon the temperature, pressure and the ratio of the elements which are used. And then xenon XeF6 can also be prepared by interaction between XeF4 and O2F2. XeF6 can also be prepared by interaction of XeF4 and O2F2, which gives XeF6. All xenon fluorides are colorless crystalline solid substances and they are powerful fluorinating agents and are easily hydrolyzed. All compounds are colorless crystalline solids and they are powerful fluorinating agents as well as compounds undergo hydrolysis very easily. So for example, when you take xenon fluoride upon hydrolysis, that forms xenon HF and liberates oxygen gas. Xenon fluoride XeF2 and hydrolysis gives xenon HF and then oxygen gas. Xenon fluorides react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroanions. Suppose when you take PF5, because of availability of vacant d orbitals in this can very easily accept fluoride ion and exists as PF6 minus. So this can be considered to be fluoride ion acceptor now. So when you take reaction between XeF2 and PF5, so if PF5 accepts fluoride ion here, it takes F minus here now. Thereby it will be XeF plus is being formed. It is now the cationic species in this. So if we have a fluoride ion acceptor like PF5, SbF5, the xenon fluorides exist as cationic species now. If you have a fluoride ion donors like say metal fluorides, they will become very easily M plus and F minus ion. If we take the reaction between XeF6 and metal fluoride here, XeF6 accepts F minus ion now. It forms anion then now. So with the fluoride ion donors like metal fluorides, they are existing as a fluoroanions then. If we have a fluoride ion acceptors, they are existing as a cationic species. Fluoride ion donors, they are forming fluoroanions. In the shapes of xenon fluorides now. So XeF2 structure. The total number of pairs of electrons which are present around xenon in XeF2 is 5 pairs now. Because if you take xenon here, so 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8 are there. There are 2 bonds. F2 means the 2 bonds are being formed here. So let us take 1 and then 2 here now. So 2 of them are bonded pair of electrons here. Remaining 3 are lone pairs present. Altogether we have 5 pairs of electrons. That is to say 5 pairs are being formed. 5 pairs means it is Sp3d hybridization. Total number of pairs, lone pairs plus bond pairs comes up to 5. It is going to be Sp3d hybridization. 3 lone pairs and 2 bond pairs are there. And it is formed in first excited state. Let us see how it is formed in the first excited state. Now when you take the ground state configuration, say it's a NS2 NP6 we have. NS2 NP6 in ground state here. So 1, 2, 3, 4. This is the NS2 NP6 state we have. In the ground state, xenon doesn't have any unpaired electrons now, so it cannot form any of the compound. In XeF2 formation here, it requires 2 unpaired electrons to form 2 bonds. So therefore, one of the p electrons must be excited to d sublevel. Means now the configuration will be in this form now. So 1 electron here and 1 in this case you are going to get. So 1 electron goes to the d sublevel. Now this is in the called first excited state we have. This is the first excited state we have. Now there are two unpaired electrons here. Hence it can form XeF2 compound. So XeF2 is being formed in the first excited state. So hybridization is Sp3d hybridization. There are 3 lone pairs and 2 bond pairs are there. So Sp3d hybridization here, there are 3 lone pairs here and 2 bond pairs. So the structure is linear. Then next compound, xenon XeF4 now. Total number of pairs again here now. It is having totally 4 bond pairs and 2 lone pairs are there. 4 bond pairs, 2 lone pairs. Altogether we have 6 pairs. 6 pairs comes under Sp3d2 hybridization we have. Sp3d2 hybridization now. Let us see how it is formed in second excited state. In first excited state, we have the configuration like this. So 2 electrons here, 2 here, 2 here, 1 in P, 1 in D we have. It is the first excited state. It is having only 2 unpaired electrons now. We require 4 because it is XeF4. So again one of them must be excited here now. So thereby the new configuration will be like this. So 1 here, 1 here, 1 here and 1 here. Now this is going to be second excited state. This is the second excited state we have. Now we have altogether 4 unpaired electrons, so it can form 4 bonds. So XeF4 forms in the second excited state of xenon. And Sp3d2 structure with the 2 lone pairs are there. Therefore the structure comes under square planar form. Square planar form. So total number of pairs will decide hybridization there now. Lone pairs, bond pairs will decide the structure over there. And to get the excited state, we require how many number of bonds are being formed by that central atom. Next, coming towards XeF6 now. Total number of pairs in XeF6 will be, that is 5 plus 1 we have. Altogether, 6 plus 1, 7 pairs are there altogether now. Because 6 bonds are being formed XeF6, still we have one more lone pair on that. So 7 are there. 7 comes under Sp3d3 hybridization. Sp3d3 we have. Now it is forming 6 bonds. So we require 6 unpaired electrons present on that. So if you have seen the previous structure, we have seen it is a second state we have. We have here 4 unpaired electrons are there in second state now. Now here, that is to say, in second excited state, this is a configuration you have in second state. 4 unpaired electrons are there. Now one more must be going towards this level. Means we have like this now. There are now 6 unpaired electrons here, so it can form XeF6 molecule now. So this comes under third excited state. It is a second state we have. It is now coming under third excited state. In third excited state, we have 6 unpaired electrons are present. Therefore, it will be in third state for the formation of XeF6 molecule. Sp3d3 hybridization. It has one lone pair on xenon present. So therefore, the structure is distorted octahedral structure we have because of the presence of one lone pair electrons on that. Now, xenon oxyfluorides. These xenon oxyfluorides, they are obtained by hydrolysis of xenon fluorides only. Xenon fluorides on hydrolysis will form xenon oxyfluorides or xenon oxides there now. So when you take hydrolysis of XeF4 and XeF6, with what it forms XeO3, xenon oxide is being formed. So XeF4 hydrolysis forms XeO3. Other products are xenon, oxygen gas and HF here. And then if you take XeF6 also, on complete hydrolysis of XeF6, you are going to get XeO3 and HF is being formed here. But when you take a partial hydrolysis, you are going to get oxyfluorides there now. So XeF6 on partial hydrolysis will form XeOF4, and on again further it reacts with water. The same XeOF4 further reacts with water and forms XeO2F2. So partial hydrolysis of the xenon hexafluoride is giving us XeOF4 and XeO2F2 here now. If xenon hexafluoride undergoes complete hydrolysis, we are going to get there XeO3 now. And during hydrolysis here, the oxidation number is not changing. Therefore, it is not a redox reaction. There is no change of oxidation state during hydrolysis. Hence, we can see they are not redox reactions. Let us now take the structures of the compounds. So, XeO3. So, in XeO3 again number of bonds, 3 bonds are there. We have 1 lone pair. Altogether 4 pairs are there. Hence, it is coming under Sp3 hybridization there now. So, Sp3 with lone pair, therefore structure is pyramidal shape we have. And it is colorless, explosive, and is coming under a third excited state now. If you see the molecule here, xenon is forming 3 double bonds are there now. 3 double bonds are there, xenon here. 3 double bonds means altogether there should be 6 unpaired electrons present. 6 unpaired electrons present. 6 unpaired electrons present is possible only in the third excited state. Already we have seen in the xenon fluorides there now. So it is 6 excited state here. So when you take the first excited state of xenon, it comes like this. The first state, excited state, we have 1 electron here and only 1 here now. The first state we have. If you go to second state here, means 1 electron gets excited there now. Then we have a configuration like this. So this will be second excited state we have now. And 1 more gets excited now. Then you are going to get 6 unpaired electrons now. Means 1 more going here. This is now third excited state. Third excited state we have now. So therefore it can form 6 bonds. In the 6 bonds here, 3 double bonds are being formed by xenon here. That is xenon here. We have 3 double bonds here now. And still we have 1 more lone pair is present on that. As regarding structure of xenon. So it is Sp3 hybridization with 1 lone pair. So pyramidal structure we have. Next one is XeO4. We have altogether completely 4 bonds are there. No lone pair. So Sp3 hybridization, tetrahedral structure we have. Colorless explosive solid. And comes towards, it is a fourth excited state we have. Because previously we have seen in third state we have altogether there are 6 electrons here now. We require here 4 double bonds, means 8 bonds we require. So we require 1 more excited state. Means here, when you have seen in the third state, we got this type of configuration there now. So 1 more must be excited here to this one. So that all will be unpaired electrons. Now this is taken as fourth excited state now. All 4 are unpaired electrons, hence it can form altogether 8 bonds are being formed by xenon. So we get like this. 8 bonds are being formed by that. So all these 8 unpaired electrons will form 8 bonds. There is a structure of xenon tetroxide we can say. Then XeOF4, xenon oxyfluoride here. So number of bond pairs and lone pairs here. So it is Sp3d hybridization we have. Total number of bonds formed are here 5 altogether. Because 5 atoms are there here, means 5 bonds will be there. Still it has 1 more pair. So altogether 6 we have. 6 implies it should be Sp3d hybridization now. And coming towards, it requires the total number of electrons 1, 2, 3, 4, 5, 6 are there. 6 unpaired is possible only in the third excited state we have. It comes in the third excited state then now. In second state, we have like this. Second state, it is having only 4 unpaired electrons now. We require 6 now. So therefore, 1 more electron must jump here now. So it is going to be now it is going to be now third excited state. Third excited state. Number of electrons are 6 in number. Therefore, it can form 6 bonds altogether. So 1 here, 2, 3, 4, 5 and 6 we have. Lone pairs is equal to 1 lone pair we have. Therefore, Sp3d with 1 lone pair forms a square pyramidal structure. So it will be third excited state. Thank you.